Hello everyone, this is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. In this session, I'm going to explain one of the application of operational amplifier, that is triangular wave generator. So while coming to the contents of this session, I'm going to revise the operational amplifier and what is the basic need of this operational amplifier and application of the operational amplifier, that is op-amp based triangular wave generator. So here, before going to the applications of the operational amplifier, first of all we have to know why we are moving for this operational amplifier circuit, even though we are having different types of single stage amplifiers as well as multi-stage amplifiers and differential amplifier. So in the case of normal amplifier circuit, when we are providing the input signal to this particular single stage amplifier circuit, it will provide the output as amplified version of this applied input signal here. Okay, so the basic parameters provided from this particular amplifier circuit is it can able to provide the required voltage gain, current gain, input impedance as well as output impedance. So these are the parameters which we can expect from any of single stage amplifier. That particular amplifiers can be designed by using bipolar junction transistors or else field effect transistor here. So we can able to design any one of the device here. So these parameters, whatever we are getting from this single stage amplifier, may not able to run all practical applications here. Okay, few of practical applications cannot be able to run by using this single stage amplifiers. So in order to overcome that, we are moving for the multi-stage amplifier. So along with that, this particular single stage amplifiers can able to amplify only low frequency range of signals. Okay, these can able to amplify low frequency range of signals. So these single stage amplifiers may not able to amplify mid frequency as well as high frequency range of signals. So in order to overcome this one only, we are moving for the multi-stage amplifiers. So in the case of multi-stage amplifiers, we can take any single stage amplifiers, that may be the bipolar junction transistor amplifiers or else field effect transistor amplifiers, and in that also we can take any configuration, common emitter or common base or common collector in the case of BJT, or in the case of FET we can take either common gate, common drain or common source amplifiers. So we can take any configuration and we can take any BJT or FET related amplifiers in order to make the multi-stage amplifier here. So how we can make this particular multi-stage amplifier means we have to cascade two or more stages of the single stage amplifier. So this one I am taking it as my first stage, and the output of this one I am giving it as the input signal. So the output of this one I am taking it as V01. So the output of this first stage is acts like an input to the second stage, and the output of this second stage I am taking it as V02. So that is applicable as the input for the third stage. So the output, the final output voltage we are taking across the last stage of the amplifier. So what is the advantage of cascading different number of single stage amplifiers here means we can able to improve all these parameters here. We can able to improve all the transistor parameters here when we are cascading the different stages of single stage amplifiers. So in this particular case, if we see the overall voltage gain of this multi-stage amplifier, we can write it as the first stage gain I am writing here it as AV1, and the second stage voltage gain I am writing here it as AV2, and the third stage voltage gain I am writing here it as AV3. So the overall voltage gain of this three stage amplifier is the multiplication of all the gains of all the stages which are present in the circuit. Okay. so that here how many number of stages are adding, that much amount of gain is increasing here. So in this particular case the voltage gain value is increasing. In this case all the stages, the first, second as well as third stage amplifiers, we are taking it as same amplifiers. That may be the common emitter configured BJT amplifiers or common source configured FET amplifiers, like that. So same configuration transistors we are taking. So instead of like this, we can also take a different type of configured transistors. That is nothing but one stage is the common emitter stage and second stage is the common base stage. So in that way also we can perform, so that we can make the Darlington amplifier. And one more case, we can take common emitter and common collector, so that we can able to get the cascade amplifier here. So these different types of multi-stage amplifiers can able to improve any one or two parameters of the amplifier here. So the normal similar coupled or similar configured multi-stage amplifier can able to improve the voltage gain, and similarly if we take the Darlington amplifier, it can improve the current gain, and if we take the cascade amplifier, it can also improve the voltage gain as well as input impedance of the circuit. So in this way, by cascading different types of configured transistors or amplifiers, we can able to improve the amplifier parameters here, so that we can able to run different types of applications by making in this way. So it is well and good, it can able to improving all the parameters of the amplifier, but even though this particular multi-stage amplifier again can able to improve the gain in mid frequency range of signals only. Okay, mid frequency range of signals only it can able to amplify. That is nothing but it will provide the highest gain when we are providing the mid frequency range of signal. If we are providing the low frequency signal and high frequency signal, means in that case it can reduce the gain and it will provide the distorted output across the final output of the circuit. So this is the drawback in the multi-stage amplifiers also. So in order to overcome this, we are moving for the differential amplifier again. So what is the basic purpose of this differential amplifier? Means first thing, it can able to amplify all frequency range of signals. All frequency range of signals it can able to amplify here. Okay. And that is nothing but it will improve the gain in all frequency range of signals. It will amplify the signal. So in order to design this differential amplifier, instead of taking single stages of amplifiers, we have to take the similar type of two transistor stages. That is nothing but that should have the same characteristics, and also the collector resistances of both the transistors are equal or similar, and the emitter resistances of the two transistors are also should be same. So in that manner we have to consider two transistors, and we have to interconnect the two transistors by common supply, that is plus VCC and minus VEE supplies. And in order to run that particular differential amplifier, we have to provide two signals V1 and V2. Those are the two input signals for the two similar transistors here. Okay, so that is nothing but it can able to amplify the differential voltage that is coming from the difference of the two applied input signals here. Okay, VD equal to V1 minus V2. So it will amplify the differential voltage how much we are providing to the input stages of the amplifier. And one more thing, it can able to amplify all frequency range of signals. So that is the basic advantage of the differential amplifier, and it will available in different configurations, that is dual in balanced output, dual input unbalanced output, single input balanced output, and single input unbalanced output differential amplifiers. So these differential amplifiers only again we are going to utilize in the op-amp design. So this op-amp is very high gain circuit compared to all these single stage, multi-stage and differential amplifiers. So among all this, it can able to provide very high gain. Okay, and the internal stages of the operational amplifier consist of the three types of differential amplifiers. Okay, there is nothing but what are the features which are having in the differential amplifier we are utilizing in the designing of the operational amplifier. There is nothing but it can able to amplify the differential voltage, and it will provide the highest common mode rejection ratio, and it will provide the very high differential gain here. So that is the main function or advantage of the operational amplifier. And one more thing here it is, this particular operational amplifier can able to perform all the operations, that is the addition, subtraction, integration, differentiation, logarithm of the given signal, and also it can able to generate the signals, and it can able to generate different types of non-sinusoidal signals also along with the amplification. So that is the basic function of the op-amp. So that's why it is called as operational amplifier. Operational means it is going to perform some operation. Amplifier means it can able to amplify the applied signal along with this particular operations. So because of that reason, we are moving for the operational amplifier from the single stage normal amplifiers here. So here we are discussing about the applications of the operational amplifier. So before going to utilize the operational amplifier in any practical application, it should follow two rules here. In that, the first rule is the whenever we are not providing any signal, that is V1 equal to 0 as well as V2 equal to 0, that is nothing but the differential voltage is also 0. So whenever the differential voltage for the operational amplifier is 0 means it should not draw or it should not source any current into the device or into the operational amplifier. That is the very important rule to design any practical application of the operational amplifier. And the feedback may be anything we can take either positive feedback or negative feedback. And the second rule here it is, the op-amp can able to do whatever it can to make the voltage difference between the two input terminals is 0. That is nothing but here we have to make always the differential voltage must be 0 whenever we are not providing any signal voltage. Why? Because if we are not providing this signal and the differential voltage is something values there means across the output of the circuit we will get some value. But we should not get this particular value whenever this differential voltage is 0. So that's why in order to make this differential voltage is 0, we have to add some external voltage source to the circuit, or else we can able to do any modifications in the circuit elements. Okay. These are the two rules to design any practical applications of the operational amplifier. So next we'll move with the triangular wave generator. So here what is meant by this triangular wave generator? It is the electronic circuit which can able to generate the triangular wave signal as its output. So this is the block diagram of the triangular wave generator. So in order to design the triangular wave generator, we require one square wave generator and one integrator circuit. And this square wave generator as well as this integrator are designed by using operational amplifier. So both are op-amp based square wave generator and op-amp based integrator circuits here. So this square wave generator, for this square wave generator, we can able to generate the square wave signal as the output here. Okay. So what is the output we are getting from the square wave signal? We are applying to the integrator here. So what is the function of the integrator here? It will integrate the applied input signal. So it will take the input as the square wave signal, and it will provide the output as the triangular wave signal. So in this way we can able to generate the triangular wave by using the square wave generator as well as integrator circuits. So now we will replace these blocks with the internal circuit of this square wave generator as well as integrator circuit. So here if we cascade these two circuits, square wave generator as well as integrator circuit, we can able to form the triangular wave generator. So here in this case, the output of the square wave generator is applied to the input of an integrator circuit. So the integration of square wave is nothing but the triangular wave. So this is the internal circuit diagram of the square wave circuit. So this part we can call it as the square wave generator, and this part we can call it as the integrator circuit here. So now we will see the operation of this triangular wave generator. So in order to see the operation, first of all we have to know the construction of square wave generator as well as integrator circuit here. So while coming to the square wave generator, in order to design the square wave generator using operational amplifier, we have to utilize both the positive feedback as well as negative feedback. So here the first resistance R1 I am taking. By using this resistance R1, some part of this output voltage, the square wave generator output voltage, will get here V0. So some part of this output voltage through this R1 resistance, we are connecting to the inverting terminal of the operational amplifier. Okay, that is nothing but we can say this R1 resistance is used to provide the negative feedback for this circuit. And similarly, next I am taking the R2 resistance. So this R2 resistance, it is also taking some part of the output signal and again connecting back to the non-inverting terminal of the operational amplifier. That is nothing but R3 can able to provide the positive feedback to the circuit. So R1 is for negative feedback and R2 for positive feedback. And what about this capacitor? This capacitor is used to provide the input signal for the square wave generator. That is nothing but what is the voltage developed across this capacitor is applied again to the inverting terminal. That is the actual input signal we are providing for the square wave generator. And this R3 resistance is used to provide the signal to the non-inverting terminal of the square wave generator. So this is the construction of the square wave generator here. So now we will see the operation of this square wave generator. So initially I am considering here, initially I am taking voltage across the capacitor is 0. Why I am making voltage across the capacitor is 0 here means initially capacitor is not charging anything, any voltage. Why? Because we are not providing any signal to the circuit. Because of that reason it is not charging. But even though the differential voltage is 0, differential voltage is 0 means at inverting terminal as well as at non-inverting terminal we are not at all providing any input signal. So even though differential voltage is 0, some input offset voltage VIOS across the non-inverting terminal is present in the circuit. Even though differential voltage is 0, some input offset voltage is present at the non-inverting terminal of the operational amplifier. So that is nothing but this is connected to the positive terminal, non-inverting terminal. So because of in this across the inverting terminal voltage is 0 here. We are not providing any signal. Across the non-inverting terminal some offset voltage is present. So this voltage is greater than this one now. Okay. This is the negative voltage that is 0 for now, and this is some positive voltage is present. So that's why because of this now my output voltage is plus V saturation across the output of the square wave generator, and the signal is like this. It is in the positive rise signal plus V sat. Okay, and similarly, so once the output is reaches to the plus Vsat, that is positive duration signal, now this particular capacitor starts charging through this resistance R1. Okay, this capacitor C will start charging through this resistance R1. So at what extent it can able to charge means how much voltage which is developed across the output of the square wave generator, that is plus Vsat. So Vc value is now plus Vsat. Till that voltage it can able to charge here, but this capacitor voltage is connected to the inverting terminal, so that is nothing but negative voltage. Okay, negative voltage is present across the inverting terminal of the operational amplifier. So once it is charging, fully charged with this output voltage, means this negative voltage is higher than this offset voltage which is present in the non-inverting terminal. So in this case, so this negative voltage is greater than this positive voltage, means obviously my output will move from plus Vsat to minus V saturation. That is nothing but my signal is coming in this way. Okay, minus V saturation. So again it is minus V saturation, means what will happen? Capacitor will start discharging through again resistance R1 here. So once it starts discharging, means what will happen? Again this negative voltage is very less compared to this input offset voltage. So in that case again it will change to the plus Vsat. Okay, so always because of the charging and discharging durations or charging and discharging voltages of the capacitor, the output it is changing from plus Vsat to minus Vsat, and again from minus Vsat to plus Vsat. So in this way the square wave generator can able to generate the square wave signal here. So this is the output of the square wave signal here, square wave generator here. So this square wave signal again we are giving to the input of this integrator circuit. So this square wave I am applying to the circuit of this integrator circuit. So in the case of integrator circuit, here if we observe, both the square wave generator as well as integrator are the inverting amplifiers. Why? Because the input signal we are providing through the inverting terminal. Okay. So, and whatever the signal we are getting across the square wave generator, again we are connecting back to the inverting terminal of the operational amplifier only. So that's why we can say both the square wave generator as well as integrator are the inverting operational amplifiers. So I have already mentioned integration of the square wave signal, it will provide the triangular wave signal. So across here V0 is equal to, we will get 1 by R1C1 integral of this V01, I will take it as V01, V01 dt here. It is nothing but output, we will get it as triangular wave signal here. Okay, so the operation of this integrator is to, it will integrate the applied input signal here with the time constant R1 C1 here. So the integration, how much amount of integration it can able to provide is depending upon the resistance R1 as well as capacitance C1 of this integrator circuit here. So that is nothing but depending upon the time constant of the circuit. And the basic advantage of this integrator circuit is it will take very large time constant R1 C1 to provide the integration. So though it is high also, it is 1 by R1 C1, so that's why it will take it as very less time to perform the integration. So in this way it can able to generate the triangular wave signal from the applied square wave signal. So this is the operation of the triangular wave generator. So if we see the waveforms of the square wave generator as well as the integrator. So this is the output we can get from the square wave generator. That is the square wave signal. It is changing from plus V saturation to minus V saturation with the time period T here. And the output of this one is the integrator. It is the triangular wave signal as the output here. And if we observe here in the integrated circuit, when we are providing the square wave as the input, see for the positive signal, for the positive rising edge of the square wave signal, it is providing the negative ramp signal. And for the negative signal, it is providing the positive ramp. Why? Because it is the inverting integrator. Inverting integrator circuit. So that's why it is providing for the rising edge, it is providing the falling ramp, and for the falling edge, it will provide the rising ramp signal. So the combination of this negative going ramp and positive going ramp will give the triangular wave signal. So this one is having the slope minus 80 and this one is having the slope plus 80. So the combination of these two will give the triangular wave signal. Okay. So now we'll see the frequency of oscillation of this triangular wave generator. We have already seen in the triangular wave generator, it is the combination of square wave signal as well as the integrator. This is the square wave generator and this is the integrator circuit. Okay, it is having two ETs. I am taking here it as A and this one as B. The final output we are getting here. Okay, so the output of the comparator A, why I am calling it as the square wave generator as the comparator means always in the operation we are comparing the voltages which are present across the inverting terminal as well as across the non-inverting terminal. So which voltage is higher, depending upon that we are getting the output across the output terminal of the square wave generator. So that's why you can also call it as square wave generator as the comparator circuit. Okay. So here we are getting the output as plus or minus V saturation signal and that is applied to the inverting terminal of the integrator. So the output of the integrator is the triangular wave and it is feedback as input to the comparator A through a voltage divider circuit R2 and R3, and again we are giving back to this triangular wave signal as some fraction of this triangular wave back to the square wave generator through the feedback network R2 and R3. So that's why in order to find the frequency of oscillation, that is nothing but in order to generate one oscillation or one signal, how much amount of frequency it is taking is depending upon the all the components in the circuit. See, this R1, C1 are the related to the integrator circuit and this R2, R3 are the square wave generator components. So that's why the total frequency of oscillation is depends upon R3 by 4, R1, C1, R2. So the total frequency of oscillation is depends upon the values of R1, R2, R3 as well as the capacitance value C1. So this is very important here, frequency of oscillation of the triangular wave generator. In order to solve the problems, we need to remember this frequency of oscillation formula as well as circuits of both the square wave generator as well as triangular wave generator here. And while coming to the applications of this triangular wave generator, in the sampling circuits, in order to perform this sampling, we can utilize this triangular wave generator. And in the thyristor firing circuits, to control the firing, we can utilize this. And in order to generate different frequency range of signals, we can utilize this. And in order to generate different sound signals or tone signals, we can utilize this triangular wave generators. And one more application of the operational amplifier is the voltage follower here. So the basic function of the voltage follower here it will give what is the output voltage what is the input voltage we are providing to the operational amplifier. The same thing we can expect across the output of that particular operational amplifier. That is nothing but here I am taking the op-amp circuit minus plus. See, this one is grounded and here we are providing the input and we are connecting back to the output here. That is nothing but this is the voltage follower circuit. So it acts like just a buffer. That is nothing but directly it will send whatever the signal we are providing here, it will send to the output of the circuit. So it will not amplify that particular signal and it will not do anything for that particular signal. So that's why we are calling it as the buffer circuit. Just it will transfer the signal to the output. So the voltage follower is having very high input impedance. Though it is sending the same signal to the output, then why we are using this one means it can able to provide very high input impedance that is required for the amplification or faithful amplification. So because of that reason, we are going to utilize the voltage follower circuit as the buffer in different circuit applications. So this voltage follower circuit, we can utilize it as the buffer circuit. So till now we have seen different linear as well as non-linear applications of the operational amplifier here. Linear as well as non-linear applications of the operational amplifier. In the case of linear applications, what is the signal we are applying, what is the input signal we are applying, accordingly the output signal is also varying. In that case, we can say it as the linear applications of the operational amplifier. In the case of non-linear applications, in the non-linear applications, the output signal is not varying linearly with respect to the applied input signal. So in the linear applications, we have seen the adder, subtractor, integrator, differentiator, all comes under this linear applications. So while coming to the non-linear applications, all logarithmic signals and all waveform generator, that is square wave generator, as well as triangular wave generator, and different types of skimmer trigger circuit and astable multivibrator circuits, and all will comes under the non-linear applications of the operational amplifier. So the specialty of this operational amplifier is it can able to it can able to utilize in all the linear as well as non-linear applications, and it can able to amplify both the AC as well as DC signals, and it can able to provide very high gain compared to the remaining all the amplifiers, and also it will able to provide very high voltage gain that is in infinity range, and it will provide very high CMRR that is also in infinity range, and it will provide very high slew rate, okay, and it will provide very high bandwidth, and it will provide differential voltage is 0 whenever both the inputs are zeros, okay, and these all are the special ideal features of the operational amplifier. So because of this reason only, in order to design different practical applications of the operational amplifier, we are utilizing this. And I have already mentioned the problems which are facing in the single stage amplifiers as well as the multi-stage amplifiers, as well as in the different feedback amplifiers and in the differential amplifiers can be able to nullify in the case of operational amplifier. And the basic thing here it is, in the operational amplifier it can able to amplify all frequency range of signals comparatively the single stage as well as multi-stage amplifiers, and it will provide very high bandwidth compared to the remaining amplifier circuits. So in this session, we have discussed that why we are moving for the operational amplifier circuit, and one of the applications of the operational amplifier, that is triangular wave generator, and also the voltage follower circuit.
Like, share and subscribe. Hit the bell icon for more updates.